There are so many stars, and so many of them are similar to the Earth, that it's just impossible that there is not a lot of intelligent life. And I say a lot, not just a little bit.
Could there be life elsewhere? We don't yet know, but astrobiology is one way to do it.
We use observations from telescopes that look at molecules in the atmosphere of a planet. Which molecules are there actually relates to what kind of different biologies are there.
What we're trying to do is sort of imagine what this broad range of life could be, because it's not limited to life as we know it.
So what we're using is Google Cloud to help simulate as much data as possible. Try to build from the thousands of data sets that we have with single observations to the tens of millions.
Google Cloud also knows how to see patterns, how to connect the dots. It knows how to link up different ideas together, and we want to do that in astrobiology, perhaps better than what a human alone or a group of humans might be able to do.
This is the moment where we'll really discover whether we're alone or not.
Hi team, welcome to a live stream here from Google in Mountain View, California, lovely glamorous Mountain View, California, in the heart of the Silicon Valley, or if not the heart, at least somewhere behind the rib cage. We're going to talk today about something that you probably don't think terribly much about, but should, and that's the interaction of the cloud and science. Okay, this may be the future of science. If you're doing science, this may be your future. In any case, I have with me an expert on the Google Cloud and how it interacts with science. Let me just tell you a couple of sentences about myself. My name is Seth Shostak, and I'm a senior astronomer at the SETI Institute, also here in Mountain View, California. And our job is to look for life in space, and in particular, whether there's any intelligent life in space. But we're going to talk about that maybe a little bit later. At the moment, I want to introduce our expert, Massimo Mascaro. And Massimo, tell us a little bit about yourself.
Absolutely. Nice to meet everyone. My name is Massimo Mascaro. I'm a technical director here at Google. And actually, I work specifically on applied AI. I have a background in physics. Actually, I was a space nerd and kind of an aspiring astrophysicist. But then I got into computational neuroscience. I got kind of fulminated by the idea of neural networks. And I started working in AI. And I've been doing that since. Here at Google, I'm in Google Cloud. And what I do is that I work with some of the largest Google clients, helping them applying AI inside their problems. So this is actually how I came to kind of work on this project, because about in April last year, we started working with NASA, in particular the Frontier Development Lab. And at that point, actually, I really kind of, my passion for space kicked in, and I decided kind of to step in and work with them.
Okay, now you talk about FDL, that's the Frontier Development Lab. Mm-hmm. That's an initiative of NASA, right?
It is.
So how does NASA interact with the private sector? Because Google, after all, is in the private sector. Yeah. So.
It is. So FDL is a really, really cool program that NASA runs. What they do is that they seek partnership with basically private companies to help out on some of the biggest challenges that NASA has. One of the big themes that FDL kind of research about, in fact, I would say is one of the most prominent one, is actually artificial intelligence applied to NASA's problem. So Google...
Give me an example of a problem.
For example, I mean, like one of the things actually that we work on this year is actually is a big problem in artificial intelligence, is how do you actually kind of automatically detect transiting of planets from the signals that you get from your space telescopes. It is a problem where, if you want, machine learning is very, very useful too, because right now actually a lot of this is done actually manually and by actual astronomers, and actually there is actually high error rates in that.
Okay, so in the cloud, you have, of course, the opportunity for sharing data. Anybody can get to it, presumably, if they're interested in the problem of looking for planets around other stars. Just to follow up on your example, they can get to the data, but they can get to something else there, too. They can get to tools, right?
Yes. So there are, I think, actually, three main things that you can get actually in the cloud. So the first one, of course, is the ability to kind of get a lot of data in and have actually kind of very, very fast access to it. That's actually kind of bread and butter, and you have to have that. The other thing is computation. So on the cloud, you can get a lot of computation to run on top of that data. And that actually is also very important. And this actually, by the way, in science is not like a super easy thing to do. I mean, believe it or not. I mean, some of the largest supercomputers today are used for science, but actually they're not very available to a lot of scientists. And then the third thing is, in cloud, actually, we built a series of like higher level of things that allow you to do things from, analytics and data processing to, AI and machine learning. There actually are tools that you build on top of like these two layers of data and computation that allow you to do those kind of things actually much more easily.
Okay, now suppose, all right, I'm a research scientist. I kind of know what they look like, right? There are a lot of them near my office. They're sitting in their cubes, they're sitting in their offices, whatever. And they're on a desk, and in the corner there's a stack of reprints that only 5 people in the world can actually understand. And they're working on a problem. Maybe that problem isn't exactly this one, right? They want to know, are there a lot of planets out there? Are there not a lot of planets out there? Okay, now in the past they would have to go get some data themselves, right? And they would have sort of exclusive use of that data, at least for a while, even if it was from the Hubble telescope or some publicly owned instrument, right? And now, okay, they need to go through those data and take a look, is there something interesting in it? They'd write some code themselves, right? It would be proprietary. They would probably spend half their lives debugging their own code, right? And they would have a limited data set, and that's how they would work.
Yeah.
Now, how's that going to happen now? I mean, I'm sitting in my office wondering, hey, look, how am I going to beat all those competitors out there?
So, I mean, a couple of things. I mean, of course, like scientific data very often actually come from sources like what you mentioned. So, for example, I can tell you that in the work that we've been doing with FDL on exoplanets, we've been working with Kepler's data that is now actually a public data set. But, there is a delay because there are certain research institutions that usually have exclusiveness on those data. For example, actually, we haven't worked yet on the newly kind of TESS data. TESS is the new, so for those who don't know, Kepler is the old exoplanet search satellite.
Old, it's been dead for what, a month?
A month, but actually, has been actually in space for 10 years or more.
Okay.
And TESS is the just newly launched. I mean, they launched it with SpaceX last April. And TESS actually is in orbit and is collecting data, but that data is not available yet. It is available to NASA and to some of these kind of research scientists, but not to to the public. So 2 things actually there. Of course, you have to have access to the data, but very, very large data sets are now becoming public. And in any case, it's always possible, even if you have private data sets, to work with Google and kind of have it imported in a private kind of setup inside the cloud. The cloud doesn't have to be public in that it's open to everyone if you don't want to. We have a lot of if you want commercial customers that have very, very sensitive data that do not share. So that's possible. But I would say that the very exciting thing is when you work on these public data sets. And now actually you have access to this data, but very often having access to the data, I can download all the Kepler data sets from NASA today if I want to. But the point is that what am I going to do with it? Because first of all, it's likely not going to fit inside my computer. Even if it does, then actually processing that data requires very extensive computational capabilities that I wouldn't have. And the cloud allows you to have those at a very, very cheap price. Now in the work actually with NASA, Google sponsored that, so that was not an issue. But in general, even if somebody had to pay it, it's actually, you only pay for what you use. Actually, Google actually will charge you by the second. Literally, kind of when you have a machine, if you have it for 1 minute and 37 seconds to do a particular computation, that's exactly what you'll get charged for. And so this actually is very transformative, I think, in science, because now I have these very large data sets that are becoming more and more available. I have the ability to kind of spawn with a very, very kind of cheap price, very large computation to analyze that data sets. And now I have this whole layer of toolings that, for example, allow me to kind of create a machine learning model or to kind of run a very sophisticated analysis that before actually would have required maybe me to get actually time slot on a very big supercomputer that maybe actually my department doesn't have access to, right? So this really kind of allows everyone to kind of do this. And I would actually kind of put it even kind of beyond that. There are actually a lot of initiatives right now around citizenship science, right? People that are not officially scientists kind of starting to do real science. And I think actually this opens up a lot, actually, the floodgates of that to happen as well.
Well, I was going to say, this sounds like taking citizen science, right, to the max. I mean, right? Because now everybody can get to the data, but beyond that, everybody has some, very competently written, presumably, tools to allow them to look at that data, so they can look for correlations, or they presumably they could say, okay, what I want to find is some sort of dip in the brightness of stars that tells me that star has some planets going around, whatever it is. Can you give me another example of the kind of things that you could use this for?
And actually, this actually is another example that we worked on this summer that is also kind of opening up another kind of stream of thought. In the second work we did with NASA, we were working on astrobiology. And one of the big problems in astrobiology is, okay, assuming there are planets out there, and now we know actually that there are many exoplanets out there outside of our solar system, we want to know actually whether there's life or not. The problem of like knowing whether there's life or not is to also understand what life is, right? I mean, there are many, many different kinds of possible life that would be conceivable. And in a sense, actually, we only have one sample, is what is on Earth. So one way around this is that you could simulate what life could look like. And there are actually various ways. The thing actually that we did with FDL this summer was to basically simulate metabolic pathways. So kind of different combinations of molecules that kind of bond chemically.
Wait, I got to follow up on this because you can simulate what extraterrestrial life might be like. Now, look, I get called up, every third week by some producer down in Hollywood, and they're going to make a film about how aliens have come to Earth to destroy downtown Chicago or whatever's on their minds. And they want to know, what are the aliens going to look like? Now, it sounds like you've got the tools to figure that out. I mean, surely that's not exactly what you mean.
No. It's much less glamorous, if you want, but actually, in a sense, actually, it's also much more interesting. A lot of like what we're thinking about life today in terms of kind of, humanoid figures and so on, I mean, we can actually go there, but it's likely, it's actually going to be very unlikely. The vast majority of life that we expect to find on, exoplanets, maybe just kind of, unicellular life, or it may not even cellular, may just be kind of some kind of chemical processes that go on that kind of signal the fact that there is actually something that kind of is self-reproducing.
Okay, so in other words, to begin with, the whole question of what life is, I mean, that's a different question, right? Yes. And there's actually no good answer to that. I mean, people say, well, life reproduces and, metabolic processes and all that stuff, uses resources, maybe moves around, right? But that's true of a lot of physical phenomena that are not alive, like fire or something like that. So, in fact, it's not that you're trying to define life. You're trying to say what chemical processes might lead to something that has the characteristics of life, right? Is that it?
It is, and in a sense, actually, it's actually a restrictive idea of life, right? Because actually there may be many larger ways of intending it. Like life could be completely digital, or could be actually not even based on necessary of chemistry, but in the realm of life that is based on chemistry, one thing that we know, at least on Earth, that life does is that it changes the chemical compositions of planets. In particular, it changes the chemical composition of atmospheres of planets. And the reason this is interesting is that we have a shot at measuring the atmospheres of some of these exoplanets. Now, to be clear, today we cannot do that yet. At least that's what my NASA friends tell me. But in the near future, I mean, apparently the James Webb Telescope may be able to do this. We may be able to detect spectra of some of these exoplanets. Okay,
well, just to clarify for people who don't work in this field, if you were to look at Earth, if you were a Klingon astronomer, right? I hope they get paid better than the earthly kind. But if you were a Klingon astronomer and you had a big enough telescope, sort of like James Webb, and you looked at the Earth with that thing, you might be able to find that there's oxygen in the atmosphere. 20% of the air in this room, oxygen, right? But that oxygen comes from photosynthesis, so they would say, oh, I don't know what's there, Zork, but all that oxygen, there must be, lettuce or asparagus or something that does photosynthesis. Okay, but that might not be the only indicator. Maybe they don't, breathe out oxygen if they're plants on another planet. Is that the idea?
That's the idea. So, and the one thing actually I want to say for people who are not kind of in this field is that, you could actually say, well, I mean, couldn't oxygen just kind of be on that planet for other reasons? Yep. Well, we know that oxygen binds a lot to a lot of chemicals. So it's very unlikely that oxygen stays in an atmosphere for a long period, because it would just oxidize most of the stuff that is in that planet and basically disappear from the atmosphere.
I mean, it turn all the iron in the soil to rust, like Mars. It becomes
Mars is a good example. Okay. So the fact that there is oxygen is because something is actively producing it. Now, there are various ways on which oxygen could be actively produced by known life systems, but we know actually of a lot of metabolic ways in which this happens. And actually oxygen, to your point, is not just the only thing. I mean, in fact, one of the things actually they told me, the astrobiologists that we worked this year, is that actually in a sense, oxygen is almost like the smoking gun of life, because, an oxygen level like the one that we have on Earth is almost unlikely to be actually just kind of due to geological sources. But there are many other chemicals. For example, just looking at the ratio of methane in oxygen or methane in other components, sulfur. There are a lot of other chemicals that could actually manifest signatures of life being on those planets. So, but going back to cloud and kind of what the problem is that very often these digital signatures of what would be the relative components of these chemicals in atmospheres, we only know them for Earth, right? And if you want to know what the signature will look like for different kind of reasonable metabolic pathways, you would have to simulate that. And this actually is what we did with Google. And one thing, again, I mean, kind of going back to the initial discussion, one thing that was very useful is the fact that these simulations are very expensive computationally. And in a sense, actually, it would take like years to run those things on just kind of even very, very fancy hardware that a normal university has. We were able to spin up on Google Cloud thousands of machines in parallel, and basically kind of the bulk of the data set that was produced in a matter of a couple of weeks by just actually spawning actually a lot of like machines inside our data centers.
I got to say, Massimo, because I know somebody, Sarah Seeger's her name, she's at MIT, and this is her job. It's to try and figure out, okay, if we can measure whatever is in the atmosphere of some planet around some other star, right, can we say that there's life there or there's not life there? Are people like that using the Google Cloud? Are they already using these tools, or is this coming down the pike in the near future?
Yeah, I think actually it's picking up. So I know that there are a number of like research institutes and kind of scientific institutions that are already using Google Cloud and cloud in general. I think actually one of the things actually we did at NASA today and this summer, and that in a sense actually I'm really hopeful that kind of creates a movement, is the fact that we proved how this can be useful. Now, one kind of other aspect of the NASA FDL program, to get clear, is that it's a program that lasts about 10 weeks. So and basically there are the scientists that come and work at actually FDL here in Mountain View, and in 10 weeks they just have to start and end. They literally have to finish their technical reports in 10 weeks. And so one other thing actually I want to throw in there is that it doesn't take much. Right? These guys literally arrived, they had absolutely no knowledge of Google Cloud at all. I remember actually we had actually a meeting at Google, and like we were basically explaining how to spin up machines, how to kind of train machine learning models, and they were, I mean, most of them actually had absolutely no prior experience, and they went actually in 10 weeks to publish some very interesting results, and actually now actually they're talking at conferences, they're publishing papers on this.
All right, so what you're saying is scientists who are already doing this, or scientists who want to do this, you know, they're not going to have to spend years learning how to do it, right? I mean, they can get trained up in a couple of weeks, and they can start doing something useful.
I think so. And I think actually this is transformative, because at the end of the day, a lot of like modern science is not anymore just kind of, you know, genius people kind of sitting down with paper and pen and kind of having like a brilliant idea. It's a lot actually has to do with data analysis, with computation, with simulation. And I think actually cloud can be transformative. Now, this actually still we haven't touched yet even into the realm of machine learning and AI. That I think it's also very, very interesting and exciting. But one thing is just actually at the basic of science, I think actually cloud can be very transformative. And I think, you know, it's just a matter of sometimes of culture and kind of being kind of used to. A lot of researchers today do not know yet these tools. They haven't experienced them. And in a sense, actually, I'm pretty sure actually that as soon as they kind of get to know them better, they'll find actually that they can change actually a lot how they work.
Let me take another specific example here. In the 1970s, NASA sent a couple of landers, the Viking landers, to Mars, you know, looking for life on our little ruddy buddy up there, right? Yeah. and the answer they came back with, I mean, this cost a lot of money. It was like $1 billion or something. I don't remember exactly. But the answer that came back was, don't know. Yeah. You know, we don't think we found any life, but of course we can't be 100% positive. Well, obviously the space agency wasn't really happy with this answer, and I suppose the taxpayers, to the extent that they paid attention, were very happy either, because you spent all this money, you want to know if there's life on Mars, and it comes back maybe, right? You don't want that. You want a definitive answer like 42 or something. You want a definitive answer. Now, if they had the Google Cloud and these tools back in the mid-1970s, do you think they would have had a better answer in the sense of a more definitive answer?
I don't know, because actually that's actually also like whether the answer was in the data or not, right? So what the cloud cannot give you is answers that are not in the data. That said, I think that for a long time in science, we've actually experienced this idea that, you know, people work on a particular problem, they do an experiment, let's say you send actually a NASA probe, or actually sometimes actually, you know, like you do like an experiment in a lab, you collect a lot of data, you process them at the best in which you can, and actually you publish a paper maybe, and that's it. that's the end of that data.
Right.
I think actually the idea that these data sets should now become public, and these data sets are becoming big, and that people now from all over the scientific and non-scientific community can go there and relook at those data. It means actually we can now start squeezing actually much more information out of the same data sets. And actually we can both validate better our research result, and we can also, if you want, find things that actually had gone undiscovered. I mean, case in point, Kepler data, right? Kepler has been there for 10 years. And with the help of Kepler, NASA has been able to declare, I don't remember the number, but I think actually it's north of 2,500 planets, exoplanets, if I remember correctly.
Well, a little more, actually.
Yeah,
but,
a little more.
A lot.
But last year, actually, Google kind of took that data set, and this is not kind of part of this FDL, this was Google Brain, our AI research department, took that data set and they basically applied machine learning to it. And they did discover a number of exoplanets that had gone undiscovered. In fact, they discovered an entire exoplanet system that looks quite like the Earth, that have completely gone undiscovered. Now, I mean, on one side is the ability to have access to the data, so that's very important. And I think actually NASA is doing an excellent job in making all those data sets public. And I think a lot of other institutions and even kind of university labs should just kind of follow suit. And some are, but like even more. Every data set, in my opinion, in science, especially if it's publicly funded, should be public. But then that's not sufficient either, right? Because now I have this gigantic data set, and there is no way, if I don't have access to the NASA supercomputer, I can actually extract information from it. So the idea that now actually, as you know, somebody, I mean, the guys at Google actually, you know, this was done actually with an astronomer at the University of Texas, if I remember correctly. But the other guy actually here at Google was just an AI engineer. And you know, they basically sat down together and said, okay, let's reanalyze this. And they found exoplanet that got missing. So I think actually this is a great opportunity for us to extract more information out of the data sets that very often costly we collect. And actually to also understand better what's sometimes actually wrong. Because like maybe sometimes actually the problem is that an analysis that has been done actually may be wrong. And like the idea that other people can look at the data actually makes it much more verifiable. That is actually one of the principles of science.
Okay, you know, there are coming down the pike some really big telescopes, right? We're talking about astronomy here a lot, but you know,
that's nice.
Well, that's right. There can be telescopes that can look at the entire sky every 4 days, that sort of thing. You know, see things that we've never seen before. I mean, you know, there could be flashing lights in the sky. We would never see them because the telescopes are never looking in the right place at the right time, right? So we're going to have instruments that can do that. We're also building these huge telescopes with mirrors that are 20, 30 meters across, and obviously they're going to be able to do things that our current telescopes can't. So the instrumentation is certainly getting a lot better, but it produces enormous tons, mountains of data that nobody can go through anymore. This is not like in the old days, you know, when I was a kid, just before the Crimean War. When I was a kid, you know, you would go to the telescope, you put a photographic plate at the back end of it, you'd make a photograph, and then that plate would go in your desk drawer. Yep. Nobody else could get to it, nobody else could look at it, and maybe you did never look at it, right? Yeah. So obviously that's going to change. It sounds like the researchers are going to become data scientists.
I think actually more and more, I mean, I think actually in part they already are. If you think about how most of the research I have done personally was really at the border between data science, data analysis, and actual kind of, you know, trying to, in my case, actually I was studying computational neuroscience. I was trying to understand how the brain works, but it was a lot of like heavy data analysis. But the other aspect is that, you know, these data sets, to your point, are becoming more and more gigantic, and they are more and more complex too, right? Because I mean, some of these telescopes require you to do all sorts of processing to this data, and this processing may sometimes actually kind of change the data. So sometimes you have to do different kinds of pre-processing. This actually was the case of Kepler, for example. And so like the idea that you have now this vast computational infrastructure, this vast analytic infrastructure, and then actually we can talk a little bit about machine learning as well, because I think actually that's also going to play a huge role there. I think actually that's going to be transformative. Now, one last thing actually on this point is the fact that I think more and more we're also kind of starting to see kind of data collection happening outside of the realm of like gigantus kind of instruments that kind of, let's say, NASA or ESA actually deploys. There is an interesting project that I got kind of to know about where actually they're putting actually these kind of small telescopes. These are kind of almost amateurish telescopes, basically all around the globe to track these exoplanets. And the idea is that, you know, tests actually will only look at a certain patch of the sky for 28 days. at a time. And so maybe actually these other telescopes will pick up from that and kind of start doing this. And again, this actually augments these data sets and becomes really fundamental now to be able to go across data sets. Not just kind of being able to apply the big guns of supercomputers or the cloud into a particular data set, but being able to kind of spawn between data sets that very often have very different shapes, forms, and they need actually very different kind of pre-processing and ability to parse. So that actually is also is going across data sets is going to be very transformative.
Well, I have to say, I mean, in my line of work, you're looking for a radio signal or a light signal coming from ET, and we get lots of signals. It's not like in the movies, right? You're sitting around looking bored, and suddenly, you see a spike on a screen, and everybody jumps up and starts screaming and calling up the press and all that sort of thing. What actually happens is every 10 seconds you get a signal, okay? But those signals can be very, messy looking, right? And AI might be just the ticket to sort through those millions and millions of signals you're getting every day and decide, okay, this is interference from a satellite, this is maybe ET, this is not ET, that kind of thing. I mean, personally, this sounds like a very attractive thing. We've been talking a lot about astronomy, space research. Can you give me another example? I'm just thinking there must be huge data sets out there which talk about various diseases, people who get a certain kind of cancer, and this is maybe their diets or their lifestyle or something else, and nobody has the ability to see if there's a slight correlation with maybe eating broccoli and getting cancer of the elbows or something like that. I mean,
those actually are big topics. You may have heard Google actually is very vested into health. And we're working a lot in it. Actually, very recently we created a whole division called Google Health that kind of will work on those problems. Some of the early results in that area are kind of mind-boggling in that it's not only about the fact that you can now actually kind of infer across very, very large data sets and understand diseases better. Is the fact that very often you then actually get also diagnoses that are much more democratized. So to give you an example, one of the work that Google is doing is to basically understand from images of the eye, of your retina, whether basically they look at your kind of your blood patterns there, and actually they can infer actually whether you have certain kinds of diabetes. Now this is transformative because if you can do this for real, and this is actually still very experimental and it's kind of still has to be a lot verified, but if you can start doing this with a camera on a smartphone, that means that somebody that is, let's say, in a poor region of the world and hasn't access to kind of super good kind of health systems and doctors, would just kind of be able to point his phone at his eye and kind of know something very, very important about his health. It also, of course, actually even kind of in rich countries where we have access to healthcare, it means actually much easier prevention. And I think actually that's going to change a lot of things. Now, going back to the problem, again, you can do this if you can actually build systems that are able to kind of very often understand the minute very subtle kind of patterns inside images, data set, temporal streams, whatnot, right? And so that's actually where kind of very often you need to kind of do very extensive machine learning on very large data sets, because in order for you to detect those patterns, you have to kind of be able to kind of identify those patterns into very large data sets, and that's again.
So this brings to mind a couple of possibilities. One is in the diagnosis realm. I'm fortunate. I live in, here in California, and if I don't feel well, I can go to my physician, and he's seen me for years. And as soon as I, walk into his office, he already has made some analysis of me because he knows what I should look like, that kind of thing. But I think it's already the case. I mean, there've been some demos of this, right? That if you let the AI do the analysis or the diagnosis, that it might be a little more accurate than the human physician because it doesn't forget all those rare conditions that the physician has because they've never seen them. So there's that. Yeah. And then there's the question of, indeed, if you're in a part of the world where you don't have access to that kind of healthcare, that maybe your phone, which allows you to maybe do some of these measurements, send that to the AI, and then it diagnoses you, and you get a better level of healthcare. Right?
Again, I mean, this is still very early times, and this is actually still very much in the domain of research and science. But I think actually this is one of the transformations that is going to happen in healthcare. I do agree with you that very often actually, today healthcare, I mean, while we have wonderful doctors and the healthcare science actually has improved as we probably could never have dreamt even like 20, 30 years ago, I actually we know that there are actually a lot of like differences between doctors. I mean, and the fact that the doctor is a human person, a human being, is a factor, right? I mean, you know, your doctor may have, you know, like himself a health issue the day before he's visiting you, and maybe he's not actually completely kind of at his best, or he just actually may have like a worry because I don't know, his son actually kind of had an argument with his son actually the night before visiting you, and again, that's one issue with
Well,
humans,
we'll have
right?
a good bedside manner. I mean, that's the question you probably get all the time, right? I like my doctor because he jokes around with me, right?
That's it, yeah. But in a sense, actually, what I'm saying is that machine learning is completely kind of abstract from this. If you have a machine learning that works, it will work in a very consistent way. So that's probably, but of course, actually, we don't have yet like kind of holistically kind of machine learning systems that can even kind of get close to match current doctors. But that actually is where a lot of research is going right now, because it is going to kind of transform completely the field. Now, going back to science, I mean, the part ahead of like the doctor kind of giving you a full diagnosis being driven by an AI, I think is actually doing a lot of research into applying AI to medicine. And this kind of goes into the discussion we're having about science, because those AIs always come from like you having kind of churned through a lot of data and having mesh whatever kind of the AI is kind of in this case predicting or diagnosing with what you know is true. And actually this requires a lot of work in actual basic science to start with.
We're getting some questions from the viewers.
Okay.
And here's one. Could you explain the usage of the Google Cloud tools in the context of the NASA Frontier Development Lab for its challenges, which are in the fields of EXO and Astro? So you might want to explain what EXO and Astro are. But
yeah, so those are the two things actually we touched on. So EXO is our exoplanet search work with FDL, where we were basically trying to train machine learning algorithms that would detect exoplanet passage into the data from Kepler and then kind of tests. And Astro instead actually is the astrobiology work. It really was two streams of work. One stream was about simulating these metabolic pathways to understand what, again, life could look like on these exoplanets. And then the second part was simulating how those metabolic pathways would affect the spectrum that you would, the spectrum is basically the different colors that you basically see, the different frequencies of light that you see actually as light passes through the atmosphere. And when you actually have that phenomenon, you can actually detect what kind of chemicals are inside the atmosphere. Of course, there is a lot that goes on inside this process, and so what is in the atmosphere doesn't kind of correlate one-to-one with what the spectrum kind of look like. And so the second part was kind of really kind of characterizing this kind of life signature as basically spectrum of planets. So going to the question, the tools actually that we use actually were kind of very wide spanning. So on one side, actually, we, as I said, actually, we had actually all the data kind of come into Google Cloud. We spun a lot of computation. So a lot of the simulations have been run inside Google Cloud. We took some very, very sophisticated codes that actually NASA had developed for example, simulating atmospheres. And we basically kind of adapted them to run on Google Cloud. And then we run them at very, very large scales. Then the second part is that those machine learning models actually had to be built. So on the machine learning side, a lot of the researchers actually use extensively something that is becoming very, very popular in data science and kind of in general ML research. Is the ability to kind of write notebooks. Now, for those of you who are not technical, a notebook is basically a document where you can basically put code and execute in it. And you can actually kind of have graphics kind of being done inside that document. So we had actually a system that would allow our researchers to kind of spawn their notebooks inside our infrastructure and then kind of run machine learning through that. Also, like Google actually provides a number of tools to do what is called serverless training. That is, you can basically submit a piece of code to Google Cloud and basically say, this is my algorithms that I need to train, and that's actually where the data is. And this service that is called Machine Learning Engine, ML Engine for friends, will basically take this code and automatically train it by actually spawning the necessary machines on the backend. So this was very useful because, again, you don't have to care about how many machines I have here or there and actually kind of spawning up the machines with the right environments. So these actually were the main basic tools. Now, of course, as part of this, those researchers, and actually this is actually one thing actually I care a lot in terms of people understanding, they loaded into Google Cloud a lot of like open source code and kind of scientific libraries that they found useful for their work. And this actually is the cool thing. I mean, you don't have to think about, okay, I have to do this work on Google Cloud, so I'm going to kind of let go all the tools that I'm familiar with, and I'll kind of get to learn all these other tools. And maybe, you know, Google Cloud is not made for astrophysics or chemical research.
So it doesn't involve a complete reset of your career.
It does not at all.
Okay. Then let me ask, because obviously people want to know, okay, this sounds great. Can you point to some concrete results? I mean, you know, has the Google Cloud published a paper? Is the Nobel Prize Committee calling up? I mean, maybe the cloud is going to get to go to Sweden.
Yeah, so like, first of all, I mean, like one thing actually I want to kind of make sure is clear is that these were actually researchers working for this program, and actually they are actual researchers that work very often in universities. They're usually kind of postgraduate students or postdocs or some actually assistant professor that was mentoring. So as Google Cloud, we're not gonna publish a paper. Those researchers will be, and there are a few actually that are coming down the line. In terms of concrete results, I'll mention a couple of things. The first one is on the exoplanet search research. The team actually was able to train a model to recognize those planets inside the Kepler datasets, and then actually we simulated the dataset for tests. So again, as I said at the beginning, we don't have yet the test data, so we couldn't run it there, but we simulated a dataset from tests. NASA has a very, very sophisticated simulation of what test data will look like, and they were able to train a model on that on one side is more accurate, at least in percentages, than what we know are the accuracies from the previous models that have been attempted, including the one from Google AI that I was mentioning before, and including actually the human performance that is currently estimated, that is Astronomer kind of looking at the data. So the model was more accurate, and I think actually that was kind of course, a great result. But to me, actually even more exciting, the model ended up being a couple of order of magnitudes smaller than the previous attempts at models. That is, it's a very small model, it's very compact. And what this allows is now actually to consider kind of running this in line with data collection. Because before actually, a lot of those models actually were pretty heavy and they required a lot of kind of computation, so they couldn't have been run kind of as the data arrived. Being able to run a model as data arrives kind of opens up a number of possibilities. For example, what I mentioned before, if there is actually a particular detection on test data as basically the data set is getting streamed, it means actually you can now alert other telescopes or other researchers about that potential detection. And it means actually collecting other data from maybe kind of other sources that could confirm or deny that particular planet, or maybe kind of extract other characteristics. One of the things that I mentioned at the beginning is that tests actually will only look at a patch of the sky for 28 days. One limitation of this, and this actually is not completely true because there is a patch where they look actually for an entire year, but in those patches, you only kind of get to see planets that have very, very short orbits, right? Because the planet has to go around.
Inner planets.
Exactly. And, sometimes actually you could see a transit, but then you don't get to see the second transit as it comes around because it's taking too long. But this actually could be like great candidates, for example, for NASA to now kind of say, hey, we have these potential kind of candidates of planets. We don't know, A, whether they're real planets or not, B, how long actually will take to retransit again, and maybe we can have, again, citizen science, maybe, or other telescopes or other researchers take on that and kind of augment the test data sets.
Massi, I mean, clearly this is kind of revolutionary. Maybe I should excise the words kind of, right? This is revolutionary. I mean, it seems that we're at the beginning, where we've opened a door to a whole new way of analyzing data and learning things about the cosmos, but about nature in general. Have we kind of reached a tipping point? This is philosophical, but do you figure that, 500 years from now, people will look back at the beginning of the 21st century and say, the most important thing that happened then was not reality television or anything like that. It was the beginning of AI applied to real world problems.
I think actually this is really kind of, we're at the tipping point where this actually may happen. I could actually tell you that, again, and I work in AI in a much broader, if you want, kind of spectrum of things than science itself. AI is changing a lot of the way in which we think about problems. And science is one of the problems that we as humans think of. It's probably one of the most important ones because it's about understanding our universe and ourselves. But AI is really kind of at a tipping point where, if you want, it's now starting to lead to results where we can now solve problems in a very, very different way. Now, for science in particular, I think going back, I don't know in 500 years, but going back, we could really see that, starting from the 90s and then kind of in the last 2 decades, more and more kind of, if you want, computers have been applied to science. I mean, they go back, the initial computers were almost developed for science. But now actually it's becoming so prominent that kind of the idea of doing science without computers is completely preposterous today. And I think actually in a few decades, it may be that the idea of doing science without AI would be as preposterous as today is the idea of doing science without computers.
But what about doing science without the scientists? I mean, how far can this go?
So this actually is an interesting point. I'll tell you actually kind of an anecdote on this. So during one of the final technical reviews that we had with the Frontier Development Lab with FDL, there were actually a number of course, NASA researchers and other professors, and the teams actually were showing some of those results made with AI. And there were actually a lot of questions about, if this AI is predicting, so for example, there was one study actually about predicting kind of solar activity, and actually where they would actually be able to predict much better than the physical models that the scientists had basically created for that. And one question is that, this thing is predicting better than we are doing, but it's not really explaining what is going on. And at the end of the day, in science, we want to understand the mechanism, we want to understand the physics behind it. So I think actually that, at least in the spectrum of what we know today, of what AI is doing, there is a lot of space for scientists, because eventually kind of these tools will simulate a lot of data, may actually be able to detect patterns, may be able to refine data sets in a way that we're not able to do as scientists, as humans. But at the end of the day, we also want to, science is really about understanding the why. Is that really kind of going back to that kind of physical law, or understanding actually the mechanism?
Well, you're talking about insight here, right? Newton didn't have AI working for him. He had his brain, and it turned out that was good enough to understand many of the, but he didn't have huge data sets, right? He had very limited data sets. Now, let's take a field such as, you know a lot about, that's neuroscience, right? They said the most complex thing in the universe is the human brain. This may be an insult to the Klingons, but but who's to say? And I suppose that at the very small level where you have individual neurons and so forth, and synapses and all that stuff, that you might understand the chemistry, you might understand the physics of what's going on there. But that doesn't mean that you understand how thinking works, because that's very complex. This sounds like a perfect application of this new technology, but will it provide indeed the understanding of what happens, or does it just give you a model and you just input a lot of data and now you can tell what the next thought is?
Yeah, so this goes to what I was saying before. That is, right now actually you could, there are applications of AI, I believe, in neuroscience as well, where they would actually start predicting actually what neurons does, or what actually a group of neurons does. However, it doesn't explain necessarily how that works. So I think, it goes a little bit into philosophy. It's a very important thing that today actually we don't get to do with AI. However, in the context of brain, I think it's even more, if you want, involved. Because in a sense, what we're trying to do with AI, in a certain sense, is to create artificial intelligence. That's what the word comes about. And one of the big questions about the brain is, what is intelligence and how does it work? If you can actually create alternate versions of intelligence, they may not have anything to do with how the brain works, right? It still gives you a lot of insights of what intelligence could be, or how intelligence could work, or what are the limitations of intelligence in certain areas or others. So I think actually for neuroscience, I would say there is the data part, there is the prediction part that is the same as with all sciences, but then the specific problem that you solve when you study neuroscience, or at least one of the specific problems, it's very, very close to what the essence of artificial intelligence is. And so,
is that sort of like 100 years ago, a little more now, when they were trying to build flying machines? They tried at first to imitate birds. We'll have wings that flap and so forth. That turned out not to be the right approach, right? They developed something where the wings don't move at all, and you just have a big propeller in the front. That's not the way. Very few of the birds in my backyard have propellers, right? And yet they could make machines that could fly pretty darn well.
Yes.
But in the end, that actually gave them insights into how birds fly. So are you talking about something like that, where you build a machine that can do some sort of thinking process, but it doesn't work at all like the human brain, but that might be helpful?
So if you want, like a jet engine is not very similar to a bird, even if it has some kind of characteristics. And a helicopter is completely different than a bird. However, the principle that make things fly apply. And in a sense, actually, kind of, if you go to the very kind of bedrock of what flying is, of how you generate lift, you can actually learn a lot from birds, but you can learn also a lot from helicopters and jet engines. So the idea here is that our brain is a way of doing intelligence. And if you build another way of doing intelligence, maybe by completely different means, that may actually still give you insights about the bedrock of what intelligence is and how intelligence works. Now, that said, I would actually kind of, just for the public, say that the most successful way of doing AI today is deep learning, and is based on this idea of neural networks that a lot of like people that, as me, actually have studied computational neuroscience will kind of say, oh, neural networks are very different from the brain, and it's true. They're very, very different from the brain. However, they have a lot of analogies. And those analogies actually may kind of give us a hint about, again, that bedrock, about what intelligence is and how actually you can build systems that learn, right? Because at the end of the day, I mean, intelligence is a very kind of fuzzy word. But learning is something that we are much more familiar with.
Well, I mean, Google did this experiment in 2012? I don't quite remember, but they took 16,000 processors, whatever it was, and they let it loose on the internet and said, go find something, and it found cats. With very high accuracy, by the way. I mean, it found cats probably better than, any cat could find cat. I don't know. And you could say, well, that's not very useful. But of course, the fact that it could see things on the internet, I mean, so I guess that's machine learning. But I think a lot of people regard all these capabilities, right? The fact that if you're a Go player, a poker player, or a chess player, there's a machine that can beat you. They regard them as a threat. And should we be looking at it that way? AI, is that going to take my job? Is it going to destroy my lifestyle? What's your view?
My personal view on this is that I think actually this is one of the greatest opportunity of humanity. So actually, I see it actually as with a very optimistic take. I wouldn't work on it if I wasn't very optimistic about it. That said, I think actually AI does have dangers and does have questions that we have to solve, both in an applicative way, so like what are the constraints where you want to apply AI, and also from a societal perspective. One thing we did at Google is that we very recently this summer we're the first company to really do that, come up with AI principles. So we have actually a code of conduct in terms of where we think AI could be applied and where it shouldn't, and how it should be applied when it's there. Now, I personally don't think that this kind of debate can only be in the realm of a corporation like Google. I mean, Google, of course, has a lot of like investment and interest in AI, but is not the only player here. And I think actually we should have more of a societal discussion about this.
Is that realistic, though? I mean, 99% of the world agrees, yes, we have to have, these boundaries, whatever. But the 1% that doesn't believe in that or see some advantage to themselves, I mean, it sounds like there might be some.
As prominent kind of researcher Nick Bostrom kind of pointed out, AI is intrinsically adversarial, because to your point, it just takes 1% kind of to do the things that it shouldn't do. In a sense, this is not very dissimilar to other kind of dangerous things that we do, from nanotechnology to biotechnology and things like those. But that's actually why it's important to have that societal discussion, because I don't think actually any corporation, any institution itself on its own actually can really kind of put the right boundaries. I think it's really it's becoming more and more kind of a humanity discussion. And it's interesting because we are in a point of our history of our world where it seems actually we're kind of getting more fractured instead of kind of getting more united as a global kind of humanity. And I see actually danger in that. On the other side, this could be things actually that kind of that unite us, because to your point, I think the majority of the people on Earth would agree on a number of those things. So.
Yeah. Well, finally then, Massi, I mean, it sounds like we're at a stage in the development of technology here, a kind of analogous to the invention of the microscope, the telescope, right? These were tools that allowed us to suddenly make big discoveries. It sounds like you're saying that the 21st century, the first half of the 21st century, we might see not only the detection of lots of planets, but life on those planets, maybe even intelligent life on those planets. And in medicine, right, we might be curing all sorts of diseases that have stymied us for hundreds of years. And you wouldn't want to rule out the tools. I mean, you want to embrace those tools. What's your advice to young people who are getting interested in science and technology?
So again, I think actually it's an amazing time. I mean, I've always been very passionate about science and technology. And like when I was young, it used to be that, I mean, unless you are really lucky to go to a kind of a good university and you have access to libraries and journals, you can't really learn a lot of things. Nowadays, I mean, young people can go on YouTube and kind of watch like lessons of like the best professors in the best universities for free. And this actually is kind of great content. You guys can play with things, as I said. It doesn't take a lot of money. And by the way, I mean, there are also kind of educational programs. If you guys are interested, kind of you can ping us at Google Cloud, where we can actually give you like credits. But what I'm saying is that it doesn't take much to get and even do kind of serious science if you are interested in it. And I think actually this actually democratizes science enormously. And I'm really hoping that for the young people that are listening to us, that they'll actually get the passion for science in the right way. And now they have all the tools literally kind of inside their laptop to kind of go and do seriously it. And I think actually this is transformative. This actually enlarges the targeted population for scientists by a number of order of magnitude from what it used to be.
It sounds like we're opening doors, big doors.
Yep.
I think people will have the motivation to walk through. Massimo Mascaro, thanks so very much for speaking with us. I'm Seth Shostak. Thank you for tuning in.